Exam 2 is next Friday. I think that's the 4th. And that will cover everything up until, so no internal loads in that. Actually, no, let's not. Let's make the soft call. So up through...
for exam 3.
Yeah, exactly. Right. So up through calculating the stresses of objects loaded like a stress element, remember that? Okay, so no internal loads. And we're working on internal loads. So if anyone has any questions or anything on the stuff related to the test, I'd be happy to answer those. Anybody have any homework questions?
I was kind of confused on, I just read the quiz
Mm-hmm.
you gave us on Wednesday on what exactly you were asking.
Do you have it with you?
Yes,
I just, I want to make it clear again that this quiz, when you get the quiz, you've already done the problem. You know?
Was this on?
That, yeah, that was a homework problem.
Well, I'll just do it on the homework.
Okay, yeah, there is a solution posted. What was it?
It was sketch the deformations that would occur in the X-Y plane.
Oh, yeah, right.
Figure out which lengths increase and which decrease.
Oh, well, let's think through it. Maybe I haven't posted the solution yet. Okay, so you had this stress tensor 5, 10, 0, 10, negative 5, 0, 0, 0, 0. And you need to figure out the deformations that would occur. All right, so the Voigt stress would be 5, negative 5, 0, and then 0, 0, positive 10 megapascals. So the Voigt strain would be if you multiplied this through the matrix, you know, this. So think of the matrix as like, the compliance matrix is this. And we're multiplying that by 5, negative 5, 0, 0, 0, 10. And so if you do this multiplication, you get 5 over E plus 5 times nu over E for the x element of the strain. Are you following what I'm doing here? Okay. And then negative 5 times, so the second one is negative nu over, negative 5 nu over E.
Are those values given in the question, or is this?
Those values? Yeah, that's the stress tensor. The 5s and the 10.
Not like the nu and the E?
No, that's the compliance matrix. That's the same compliance matrix you always use. You could leave those as variables in your calculator and just plug it into your calculator, and it'll give you an expression for it. Or I guess when I think about it that way, I should have put the compliance matrix on here, but I'd be happy to write that up on the board anytime you want. But negative 5 over E. And then for Z, you have negative 5 nu over E plus 5 nu over E. And then you have 0, 0, and then 20 times 1 plus nu over E. 1, 2, 3, 4, 5, 6. Okay? And so to sketch this, all we need to know is this one's positive, this one's negative, this one's 0, and then 2 more zeros, and then this one's positive. And so now we're just going to sketch an element that has these, that deforms in these ways. So if we're using this coordinate system, we're starting with a cube. It's going to get longer in x, shorter in y, stay the same in z. So it's going to look something like, something like this, first of all. Right, longer in x, shorter in y. And then this says that the angle between the positive x and positive y faces is going to get more acute. And so you'll get something like this.
That's what the last positive means?
Yes. A positive shear strain means the angle between the two positive faces bless you, gets more acute.
So can you not just like draw the cube, like the two-dimensional cube, and just, like breathe through it? Or is that
Well, You mean with just based on the stresses?
Yeah.
You have to think a little bit about the strains because of that Poisson's effect. In this case, if you would have done that, you would have gotten the right answer, I guess. But you have to be careful of that Poisson's effect. If this was only, like, if you have a stress that, if you only have a X normal stress and nothing else, remember that all of the normal strains are going to be non-zero because of the Poisson's effect.
XX positive means on that axis it gets
Yeah.
bigger and then the y half compressed.
Right. Yep. And then the corresponding principal stress tensor. So then you just take the eigenvalues. I don't know what those values are, but well, can someone punch that in? So the principal stress tensor, or a principal stress tensor,
negative 11.10.
okay, so if you wanted to be clever, you could say in the principal coordinate system, it goes from this to this with no angle changes because you have you don't have any shear stresses in that case, and then you don't have to worry about but there's still a Poisson's effect. I think I said just do it in the XY plane, so you didn't have to draw the Z deformation anyways. But any other questions about that one? Okay. Any other questions about stuff related to the test? Okay, so last time I introduced this problem where you had a beam with a roller at the center. A force there of 1,000 newtons and a torque at the end of 500 newton meters. The length was 2 meters total. So the question is, what are the internal loads, tension, shear force, bending moment, bless you, and torque as functions of x? And we went as far as calculating all the external loads. We just haven't done the internal loads yet. So if you isolate the whole thing, the external loads you get are 500 newton meters there, a force vector of negative 866, negative 500. A 1,000 Newton force at the roller, and then the external loads that were given, 1,000 newtons and 500 Newton meters. Okay, so I'm going to go through the internal loads, but first let me give just a set of general steps for solving these kind of problems. So general steps for internal loads problems. So after you calculate the external forces, and identify the n boundaries between the subfunctions, and how do you identify those boundary points? What are the candidates for those? Yep, endpoints. Point forces.
Distributed loads change.
Yep, the distributed load function changes, and then also point couples. Okay, so after you do that, then for each of the n-1 cuts, each of the n-1 cuts, isolate a piece of the member, a piece of the beam, from the far left endpoint to a location X, where that X has to fall between two of these boundary points. Okay, so as an example, if this is the member and these are the boundary points, then you're going to isolate a piece of the member like that, okay, where this distance is just referred to generally as x, and we're going to calculate everything in terms of that variable x.
X goes from the first red dot to the second red dot, but not including the second red dot.
Yeah, because it doesn't really go from the red dot. It goes always from the far left endpoint. So the only part that cares about where the left part of what we isolate doesn't care about where the dots are. It always goes from the far left. The right end of what we're isolating falls between two red dots always. Never, and that X never represents this red dot, and it never represents this red dot. It's always in between. Second, draw a free body diagram. including the internal loads at the cut. So in that example, your internal loads would be a tension T, shear force V, bending moment M, and then a torque T. Then the equations, Newton's second law, the moment equation about the z-axis, and you need to think of the origin at the far left of the member, far left of the beam. And then the moment equation about the x-axis. We're not doing y, just x and z. Yeah. So if that thing like bent down or up, that would be about z, and then about x is the torque. Okay, so our coordinate system is always going to be this. The x-axis along the long axis of the beam, y-axis there, z out of the page, and the origin is always at the far left of the beam.
Quick question.
Yeah.
So if you first analyze the far left section and then analyze the far right section, would the origin not shift to the middle of the beam again at the far right?
That's right. You don't ever. So the first cut is this, but here's the second cut. The second cut, let me draw these points in, isn't from here to somewhere in there. It's all the way from the left to here. And so we'll keep that coordinate system location in the same place. Okay. And so the x value itself only refers to the right end of the beam, right end of the cut of your isolated piece. Okay. So for solve for the subfunction, subfunctions T, V, M, and fancy T. And then the final answer is the piecewise functions that you get from combining all of these subfunctions. So it's a piecewise function for T, a piecewise function for V, piecewise function for M, and fancy T. Made up of n-1 subfunctions for each. And then a lot of times you'll want to graph that. Okay, 4 steps, that's all. So let's go through this example. we have a torque of 500 on the left, a force vector of negative 866, negative 500. At the middle, we have a force vector of 1,000 up. Over here, we have a force vector of 1,000 and a torque of 500. So we have the external loads. We have the external loads. Now we need to identify the end boundaries between subfunctions. So those boundaries are at the endpoints. And then any place that you have a change in a distributed load function while we don't have any distributed loads, or where you have a point force or a point couple. And the only other place that isn't an endpoint is here. So n is equal to 3, which means we're going to have 2 cuts. And our piecewise functions are going to be made up of 2 subfunctions. For each internal load. Okay, so cut 1. It's going to go all the way from the left endpoint to some x value where x is in between these 2 points. So x has to be somewhere between 0 and 1. So there's all this going on that we're not aware of right now. We only care about this piece. And so what's acting on this piece? The 500 Newton meter torque, and then there's a force vector of negative 866, negative 500. What about this 1,000? Nope, that's not over here. That's somewhere else. So the only other thing that we're worrying about is the internal loads applied to our chosen piece by the connected piece. And so that is a tension, a shear force, a bending moment, and a torque. Okay, so Newton's second law says add up the forces, negative 866, negative 500, plus this t is in the positive x direction, so that's positive t0. V is in the negative y direction, so that's 0, negative v. And those are equal to 0. So that tells us that over this whole interval, from 0 to 1, the internal tension is equal to 866, and the internal shear force is equal to negative 500. And now let's think about the moments about the z-axis. And remember, I'm putting the coordinate system over here. Okay, so does this 500 Newton meter couple produce a moment about the z-axis? Nope. What about this force? No, because it's acting at the about point. The internal bending moment, M, does. And then V does. What's the moment arm for V? X. And is that a clockwise or counterclockwise rotation? Clockwise, so that's minus. Now what about T? Does that produce a moment about Z? No, because its line of action goes right through the about point. So no moment. And then what about the torque T? Nope. So this is it. So M is equal to Vx and we have a value for V here, so M is equal to negative 500x. And now the moment equation about the x-axis. Does the 500 produce a moment about the x-axis? Yes. What about the force vector, negative 866, negative 500? No. What about M? What about T? What about V? Nope, just, so then this torque T, fancy T, is the only thing left. And so the torque over this interval is just equal to negative 500. Okay, so these four subfunctions are valid for x between 0 and 1. So now we're going to do our second cut and figure out what the subfunctions are that represent this member for x from 1 to 2. Okay, and then the combination of those two is the piecewise function that represents the whole thing. Yeah, well, shear is just yeah, it is. It's just a force that's counteracting other forces. So if you only have a point, you know, that V is just a reaction to this 500 Newton force acting down here, and that doesn't change. And the moment arm doesn't affect forces, you know, and so so this V is just counteracting this 500 the whole way along. Okay, so now cut 2. Any other questions about that cut?
It is changing.
M is, but not V. M is changing because as x changes, the moment arm changes. But V comes from Newton's second law. And, you know, in Newton's second law, there's no such thing as a moment arm. It's just about forces adding. Okay, so the second cut, what's the interval for cut 2? Yeah, x between 1 and 2. So here's the whole thing. So what are we going to isolate? Yeah, we're going to, so yeah, it's going to be, we're going to go all the way from the left endpoint, which is kind of a key thing and can be confusing, and then we're going to go to some x value that's at least 1 and something less than 2. So we're going to isolate something like this. And so the loads acting, we have the torque of 500. We have the force vector of negative 866, negative 500. What about the roller force, that 1,000 Newton force? This time it's in there. These two, we still haven't gotten all the way over there yet. What was that, 1,000? I'll just leave it like that.
866 and 500, they can calculate the whole thing, right?
Yeah.
1,000 and this 1,000.
The two that are in black? Those are the external loads, so that was the first step we did.
Like counteracting the two
Right.
upward and
Yeah. Okay, so we have these, and then we have the internal loads. So T, V, M, and fancy T. Iced tea. A high school friend of mine was a producer for one of Ice-T's albums. Isn't that cool? And he's in the commercials like his producer name is Bionic, and it's like this Ice-T video, and then it like shows him, and he's like, Bionic, bitch. It's so funny. And then it goes back to whatever. He's just in it for like 2 seconds, but that's not very nice language. He only said 2 words, and 50% of those words were obscene.
Or you could just be referring to,
It could be. Okay, so Newton's second law. Says negative 866, negative 500, plus 0, 1,000, plus T0, plus 0, negative V is equal to zeros. So the internal tension is equal to 866. The internal shear force is equal to positive 500. And now we'll do the moment equation about the z-axis. So does the 500 produce a moment about z? No. The force? Not that force, because our about point is at the left. The 1,000, what's the moment arm for that 1,000? It's not x because it stays put. You know what I mean? That force is just a point load that no matter what x is, that 1,000 is acting 1 meter from the left endpoint. Okay, so that's an easy thing to mess up on. But so we have 1,000 times a moment arm of 1, and would that produce a clockwise or counterclockwise rotation? Counter, so that's positive. Then plus m. And then the only other one that affects this is v. What's the moment arm for v? X. So Vx, and is it plus or minus? Minus, and it's always, Vx always comes in as a minus. Okay, so that's it. And so solve for m.
You're doing it from right to left.
the force, so that V, like trying to figure out the sign.
Yeah. You said
The
it's
about
always-
point is here.
But I mean, if you did it the other right
Oh.
to left, is V then always
Oh.
positive, or is it still always?
Actually, it would still be always positive because the moment arm would be going the other way.
Then it would always be negative.
Yeah.
So either direction.
Oh, clockwise. You're right. It would switch. Yes. I'm sorry. Yep. It would be, so it's always, oh no, it's clockwise both ways.
Yeah, it's always.
Yeah, either way you did it, it would be minus Vx. But I think, why not just do it the same way every time? So let's just always do it from the left. We could do it that way, but,
Okay. That made it.
okay. So m is equal to Vx minus 1,000. We know what V is, so m is equal to 500x minus 1,000. And now the moment equation about the x-axis. Does the 500 produce a moment about the x-axis? Yeah. Does that force vector? No. So the only other thing that does is the torque T. So we have 500 plus T is equal to 0. So T is equal to negative 500. Okay, so let's think about what these tell us. So this new set of subfunctions is valid for x between 1 and 2. Okay, so tension is 866 for both of them. So tension as a function of x is 866. So as you go across the length of the beam, that internal tension doesn't change. And notice that the way that tension works is if it's positive, it means that it is actually in tension, just like a positive stress is a tensile stress. So this is a tension you can use directly in the you can use this tension directly in the in a stress calculation to calculate a tensile stress. You don't have to mess with the sign. And then now the shear force, it's negative 500 for the whole first half, then positive 500 for the second half. So the shear force as a function of x is a piecewise function that's negative 500 newtons for x between 0 and 1, and positive 500 newtons for x between 1 and 2. The bending moment no thanks. Oh, sure. You do? They're for me. I was just thinking, like, wow, my voice made it exactly to the end of the week. And then just gave out like a heroic marathon runner. Okay, so for the... It's not me, it's my voice. I just tell it what to say. So mx over the first half of the beam is, what was it? Negative 500x. And then over the second half of the beam, it's 500x, is it minus 1,000? And then the last one is the torque. That doesn't change. That's just negative 500 the whole time. So fancy t is a function of x is equal to negative 500 Newton meters. Yeah.
So it's like leave units off for the
Yeah. So that's a little inconsistent. I don't know.
That's the only one that's a function of x.
Yep. Okay. And so you could also plot these out. So if you plot the tension versus x, it's positive 866 the whole way. If you plot the shear force versus x, it's negative 500 and then positive 500. You plot the bending moment. This is the one that takes high school math skills to do. So it's going to go from 0 to negative 500. And then it's going to go back like this. And then the last one is the torque. And that stays constant the whole time at negative 500. Mm-hmm.
You just start at minus 1,000. Doesn't shift it down.
It does, but if you look at what we're doing is, so plug in 1, and you get negative 500, which means it starts right where this one ended, and plug in 2, and you get 0. So remember that each of those subfunctions is only valid over part of the graph. That makes it sort of a hassle to try to plot these out on your calculator. It's pretty easy to do in like Excel or something, or MATLAB, but it gets pretty muddled looking on a calculator. Any other questions about that? Okay, that's all.